So, the methodology for analyzing circuits, lecture 2.1, is going to be a method that we'll use for now. So we have all the tools we need to do some pretty badass circuit analysis. Later we'll learn a more systematic method for analyzing the dynamics of a circuit, but for now, we can use broad strokes to get the idea. It will work most of the time, but occasionally you'll need to write some extra Kirchhoff current law equations or Kirchhoff voltage law equations, or use a more advanced algebraic technique than we would like to, but for the most part it will work. Some of those edge cases motivate going to a more systematic approach, especially for more complex systems. It gets more and more complicated to do this method, but it'll let us get quite a bit of the way through electronics and thinking about circuits without any trouble. So let n be the number of passive circuit elements in a circuit, which gives 2n unknowns. So the voltage and the current for each passive element is unknown. For any active element, an input to the circuit, like a voltage source or a current source, we'll know what the voltage or current is prescribed to be. So
an active element would be like a motor or something like that?
No, an active element would be like a voltage source.
Okay.
We'll talk more about motors. That's a transducing element, we'll call it. But yeah. So for now, we're not considering those. So just for the passive elements in the circuit, there's going to be n of them, and there will be 2 unknowns for each one. So we don't know the voltage, we don't know the current of the elements in the circuit. So we're stuck with 2n unknowns, and so how many equations do you think we're going to need? 2n, yeah, so 2n, so 2 equations for each passive circuit element. So the method is this. First, draw a circuit diagram. Then label the circuit diagram with the sign convention by labeling each element with the assumed direction of current flow. It'll also assume to be the direction of the voltage drop. Step 3, write the elemental equation for each circuit element, which is Ohm's law for a resistor. For a capacitor, you might recall it was dVc dt equals 1 over C IC, right? That's for the capacitor. So these are the elemental equations. There was also one for the inductor. It's the equation that relates the current and the voltage for that element. So write the elemental equation for each of them. So that gives us n equations, right? To start, we need to get n more now. And the way we get n more is through Kcl and Kvl. So every node not connected to a voltage source, so for every node not connected to a voltage source, write Kirchhoff's current law, Kcl. Okay. And 5, for each loop not containing a current source, write Kirchhoff's voltage law. Okay? Or KVL. You probably have a linear system of 2n algebraic and first-order ordinary differential equations, and 2n unknowns to be solved simultaneously. So in theory, at this point, I could be like, do maths and solve. Usually, you guys will be able to do steps 1 through 5 without too much trouble. And then we wade into the weeds of algebra and differential equations, and then people get pretty lost in here. But recognize that if you learned an algorithm for solving these things algebraically and using differential equations, if you learned it well enough, I mean, it's literally just automatic. You can teach a computer to do it from there. So you could do it from there pretty consistently if you had it, all of your stuff in a row, if you will. So I encourage you to see 6 here, this last step, as being a necessary step to learn. Probably going to be the most challenging for a lot of you to get through with your sanity, but it's also, once you've gotten through step 5, you really you have all the equations. It's just math from there. Okay, all of your physical insights, you don't need them anymore. You're done. Like, you're just doing math. Autopilot the rest of the way. Okay. Yeah, that's right. So you probably have this situation where you have 2 algebraic and differential equations, and you need to solve them simultaneously. So the step A works every time, assuming you've got the system. Eliminate n, or half of the unknowns, by substitution into the elemental equations. Okay, so elemental equations you're going to leave there, and you're going to substitute in and eliminate half of the variables by using the Kcl and Kvl equations. So I should put a note here from the Kcl and the Kvl equations. So you'll be able to solve the Kcl and Kvl equations for some variable that you can completely eliminate from the elemental equations if you solve for it. It does take a little bit of training to identify which one needs to be substituted, but if you recognize, oh, the current through this capacitor only shows up in the elemental equation and the Kcl equation. If I solve for it in the Kcl equation and I substitute it into the elemental equation, I'll eliminate that from my equations, so I don't have to worry about it anymore. That's the kind of thing you're going to want to do. So it's easy because you can always do it by substitution. You can get rid of half of them, half of your equations, half of your unknowns by substitution. It's pretty nice. Yeah?
I just want to verify, KVL is the 1 over LV, right?
So KVL is Kirchhoff's voltage law, which says that if you sum up the voltage drops around a loop, then it should equal 0.
Oh, gotcha.
That's that one. And the Kcl is the one where you're summing up the currents into a node. So that's Kirchhoff's current law. So, so then part B, try substitution to eliminate, to get down to, I tried it 2 different ways there. Try substitution to get down to only those variables with time derivatives and inputs, okay? So that would be ideal. That's where you want to be. You're going to have some of your elemental equations will be algebraic equations. You want to get rid of all the algebraic only equations and be left with equations that are only differential equations. If you can't do it by substitution, I recommend just using a linear algebra technique. I mean, you could use Gaussian elimination. You guys have been working with systems of linear systems of equations for a long time. The fact that some of them are derivatives actually does not have any bearing on eliminating variables. You can use the same exact methods you've always used. Okay, but once you get it down to a set of first order linear ordinary differential equations, no more algebraic equations, then solve the equation simultaneously. So there's either you can do it directly as a system of first order linear ordinary differential equations, which you probably saw in your differential equations class. Hope. What?
That was freshman year.
Oh yeah. Well, hopefully that's coming back for you. Or the other possibility is it can be turned into a single higher order differential equation and then solved. So if you've got, for instance, 3 first order differential equations, you could turn that into 1 third order differential equation and solve that. So you could do one or the other. I actually don't have a strong opinion on what you do. Whichever one you're more familiar with is fine with me. Early on, we're mostly going to be focused on first and second order systems for actually full solutions. So you probably won't have to deal with higher order systems in your homework or on exams until we get to the systematic approach that we'll take later. So, but it won't be till the end of the semester. Okay, but in theory, you should be able to do it for any order system. It's just that I know it's a lot of work, so. All right. You know, let's see. Oh, it's easy enough. We can do this in one. We can do it. We'll do it. RC circuit analysis and initial value problem. So, in the RC circuit shown, let the source voltage just be a constant 12 volt source, okay? If Vc of t at time equals 0 is 0, so the voltage across the capacitor at time equal to 0 is 0, what is V out of t for all time greater than or equal to 0? Where V out is shown on the diagram. Okay. So, what is our first step? The circuit diagram was already done, right? Step 1, check. Step 2, signs. Well, they actually already, by they I mean I, already put the signs on here, so we don't have a choice. We have to assume voltage drops and current flows from here to there and from there to there. So, and also V out I put in the same direction of assumed voltage drop as Vc, conveniently. So, step 2, check. Step 3 was great. So let's move to the next page to do step 3. Step 3, elemental equations. We're going to have for the resistor. So there are 2 elements. So we're going to have. So sometimes what I do, it's probably good practice to do this, is I write a list of them vertically. So R and then C. So I need an elemental equation for R and an elemental equation for C. So what is the elemental equation for the resistor? Yeah, it's just Ohm's law, right? Okay. And how about for the capacitor? I drew it on the other page, right? Yeah. dVc dt equals, I don't know why pen doesn't work as well as it should, equals 1 over C IC, right? Okay, so that was step 3. Step 4 was to write the Kcl equations, right? And it says for every node not connected to a voltage source. So how many nodes are there in this circuit total?
3.
1, 2, 3, right? Now, these two nodes are connected to a voltage source. So we don't need to do KCL for those. But let's do KCL for this node, which says that if we sum up the currents going in, we have IR, and then we have minus IC equals 0, right? Which is equivalent to saying that IR equals IC. Good. Step 5, KVL. We need to write KVL for every loop that doesn't have a current source in it. And we've got ourselves only one loop. And so it says that if we sum the voltage drops around this loop, then we get 0. So we have, for instance, VR plus VC minus VS equals 0, right? So VR plus VC, because those drops are in the same direction around the loop, minus VS, because it is a gain if you go around the loop that way, equals 0. So that's another equation. Step 6. Well, let's do part A first. We can eliminate a variable with, if we look here, we don't want to eliminate the variables that have time derivatives. So VC, we don't want to eliminate. So we don't want to do that. We do want to eliminate everything else except for VS, the input. Okay? Now, if we were to plug in the fact that IR equals IC into this first equation, that would eliminate IR from contention in these elemental equations, right? So that's good. We want to do that. So we'll do that. So we'll do, I'll rewrite my R and my C. So I have VR equals, instead of IR, I'm going to put IC in there. IC times R. Okay.
Can you say that IC is equal to C multiplied by dVC over dt?
Yeah, well, we don't want to start going in loops yet. And we can technically do either one, but I'm going to actually choose the other one. I'm going to eliminate, sorry. I'm gonna go back. I'm gonna, instead of eliminate IC by plugging in IR. So dVC dt equals 1 over C, and I'll use IR. Okay, so that gets rid of IC from contention. Now, in the other equation, I can say that IR is equal to VR over R, right, if you just solve this. But I'm going to use this equation to plug in for VR. So VR is VS minus VC divided by R. All right. So now I've gotten rid of IC. IC is gone. I've gotten rid of VR. VR is gone. So I'm left with VC, which I don't want to eliminate because there's a time derivative of VC, and IR, which I do want to eliminate. Conveniently, in this case, I can simply plug IR into IR in this expression and use elimination. It's not guaranteed that you're going to be able to use elimination. You're left with just the C equation now, which is dVC dt equals 1 over C times IR, which is, the R I'm going to pull out here to the coefficient, and we have Vs minus Vc. Okay. So we've got ourselves just one ordinary differential equation, right? We don't have a system of them. It just ended up being one. Could have had a system, but we ended up with just a single one. So now we need to solve the ODE. I'm going to save that for next time because I don't want, I could just say, solve the ODE, it's first order, it's easy. But I also realize that some of you might not have seen this for a little while, so I'm going to slow down and solve it on Wednesday. Okay? All right. Welcome back. I'll entertain any questions if you have them. I mean, clearly now you know how to do the rest, right? Solve ODE.